Welcome to the robotics session, first session of robotics track. And so the first paper will be POMDP-based candy server, lesson learned from a 7-day demo. And the speaker is Marcus Hoerger. In the program is switched to the list of the names. So, okay.
Okay, so thank you very much for attending my talk, and I think I should go a little bit away from the speakers. So my name is Marcus Hoerger. I just recently started my postdoc at ANU under the supervision of Hanna Kurniawati. And this talk is about work we've done as part of the Kinova beta program, where our goal is to develop robust planning algorithms for a robot manipulation demo that we showcased at last year's SIMPA and ICRA conferences. So in this work, we are looking at the problem scenario where we have a Movo mobile robot equipped with a 6-degree of freedom Checo manipulator and a Kinect sensor, where the robot has to act as a candy server. So here the task of the robot is to obtain an understanding about its environment in order to be able to localize and pick up a cup placed in front of a table, robot. Then it has to use this cup to scoop candy from a box located next to the table. And last but not least, it has to put the cup back on the table while avoiding spillage. Now, at the first glance, this seems like a relatively straightforward problem to solve. However, there are some challenges that prevent us from naively applying off-the-shelf planners, where the first challenge is uncertain and potentially changing positions of the cup. So here we assume that the robot has limited understanding about the exact location of the cup, and we also assume that that cup can be misplaced during runtime. Now, of course, the robot can use its Kinect sensor to localize the cup. However, we found that even after doing a little bit of calibration, there are still substantial perception errors with respect to the location of the cup. And additionally, we assume that the robot has limited prior information about its operating environment, particularly with respect to the location and fill factor of that candy box. And again, the robot can use its sensor to build a rough model of the environment, but these observations are very noisy. So in order to deal with these challenges in a principled and robust manner, we formulate the task as a partially observable Markov decision process, where a POMDP is a mathematical framework from decision theory that enables autonomous robots to make robust decisions under partial observability, where the main components of a POMDP are the state, action, and observation spaces of the robot. Then we have a transition and observation function which model the uncertainty in the effect of executing actions and perceiving observations as conditional probability functions. And last but not least, we have a reward function, which is essentially our objective function that we're trying to maximize. Now, due to all the aforementioned uncertainties, the true state of the robot is only partially observable. Therefore, instead of planning in the robot state space, we lift the planning to its belief space, so the set of all probability distributions over the state space. And the goal is now to compute an optimal policy, which is a mapping from beliefs to actions that maximizes the expected total discounted future reward the robot receives when following this policy. Now, unfortunately, it has been shown that computing this optimal policy is intractable in general. And in particular, the complexity of computing the optimal policy is exponential in the number of states, the number of observations, and doubly exponential in the planning horizon. So in other words, in all but the simplest problems, we have actually no chance to compute this optimal policy. But there has been a lot of progress in the last 15 years. So nowadays, we have some very efficient, approximate optimal online solvers, where the idea is to balance optimality with computational tractability. And online solvers, instead of computing a policy for the entire belief space, typically compute a policy with respect to the current belief only, usually by performing forward search on a belief tree here, where these nodes represent beliefs and the edges represent pairs of actions and observations. Now, however, despite this progress, even the fastest POMDP solvers today have difficulties with large action spaces and long planning horizons, which basically means that our particular problem scenario is simply too large for state-of-the-art solvers. So what we do here to keep the problem manageable is we divide the whole task into 4 separate POMDP problems that are then being solved sequentially. So starting from an initial belief that we obtain using an initial scan of the environment, the first task for the robot is to figure out how to grasp and pick up the cup. Then in the second robot, the robot has to bring the cup near the candy box in a way that is beneficial for scooping. Then it has to do the actual scooping before then putting the cup back on the table while avoiding spillage. Now, the way these problems interact with each other, once one POMDP problem is solved, the current belief of the robot becomes the initial belief of the subsequent problem. Okay, so now the first problem here, the picking problem, is perhaps the most interesting one because, as I mentioned before, here we also assume that the position of the cup might change during runtime. And the robot then has to react accordingly to reduce uncertainty with respect to the location of the cup. So the way we formulate this problem is we model it as a kinematic problem, where the state space of the robot is a hybrid space consisting of the continuous set of joint angles. Then we have a gripper state, which indicates if the gripper is open or closed, and we have a grasp state, which indicates if the robot is holding the cup or not. Then the actions the robot has access to here are a set of joint angle increments and decrements for each joint. Then we have a gripper action, which opens or closes the gripper. And we have a scan action for which the robot utilizes the perception system to localize the cup. And the observation space, again, is a hybrid space consisting of the continuous set of cup poses that are being perceived after the robot executes a scan action. Then we have a gripper state, an observation regarding the gripper state, and we have a simple grasp detector. Now, as I mentioned before, a major challenge in this problem stems from the fact that the location of the cup can change during runtime. So this essentially means that the robot has to consider multiple scanning actions to reduce uncertainty with respect to the location of the cup. However, the problem with this is the robot actually has to see the benefit of reducing uncertainty. In other words, it requires a sufficiently long planning horizon for the robot to figure out that reducing uncertainty helps to accomplish the task down the line. So what we do here is we additionally equip the robot with 2 macro actions represented as finite state machines that help to reduce the effective planning horizon. Where the first macro action is the scan and approach macro action, consisting of a scan, approach, and retract sub-action. And the way this works is, suppose the robot performs a scan action, which then yields an observation with respect to the location of the cup. Now what happens is, inside this macro action, we transition to a located state, from where the robot then executes an approach action, which is a sequence of primitive actions to bring the gripper close to the estimated location of the cup. Where this action sequence is essentially obtained using methods from deterministic motion planning. Now, on the other hand, if the scan action doesn't yield the location of the cup, for example, because the cup is occluded by the arm, then we are transitioning to a not located state from where the robot executes a retract action, which again is a sequence of primitive actions, but this time the goal is to bring the arm to a configuration from where the table is likely to be occlusion-free. And then we are transitioning to a retracted state from where the robot then executes another scan action, and based on the outcome, it again transitions to a located or not located state. So now the second macro action here is the grasp and rescan macro action. So this macro action is designed to deal with failed grasps. Now, a grasp can fail due to 2 reasons. There's either too much uncertainty with respect to the location of the cup, or the cup has been misplaced during runtime. Now, in both cases, the robot has to relocalize the cup before attempting another grasp. So if a grasp fails, the robot immediately executes a scan action, and then similarly to the previous macro action, if the robot doesn't see the cup, it performs another retract action to get to a configuration for which the table is occlusion-free. Okay, so after we've specified the picking problem, we're now looking at the pre-scoop problem, where the task is to move the cup to a pose near the candy box that is beneficial for scooping. So this problem is formulated as a motion planning problem under uncertainty, where the robot has to bring the cup to a small goal area above the candy box, such that the opening of the cup faces the candy surface. Where here we are using the same state, action, and observation spaces that we had previously, minus the two macro actions. Now after this, the robot has to do the actual scooping. And in order to achieve this, we extend the state space by two additional variables, where the first variable here, the candy height, is introduced to account for uncertainty in the height of the candy surface. Whereas the second variable, entered candy box, allows us to separate the reward function into two parts, a part before the cup has entered the candy box, and a part where the cup is beneath the candy surface. Where for the first part, the robot receives a high reward when the cup dives beneath the candy surface, and in the second part, the robot receives a high reward when it lifts the cup back up in an upright orientation. So structuring the reward function in this way, the robot is encouraged to form a scoop-like motion. And then last but not least, we have the placing problem, which is again formulated as a motion planning problem under uncertainty, where here the goal is to place the cup on the table while holding it in an upright orientation to avoid spillage. Okay, so after we've specified the entire problem, the question is now how do we actually solve it? And the online solver we're using here is ABT, a Monte Carlo tree search-based method, which repeatedly samples histories starting from the current belief, so sequences of states, actions, observations, and rewards, to evaluate different sequences of actions. Now, the reason why we chose ABT as the solver here is because it is one of the fastest online solvers today. And in addition to that, it allows us to parallelize policy computation, policy execution, and belief update. So the typical execution flow of ABT is computing a policy with respect to the current belief, which then yields an action the robot executes. And after the action has been executed, the robot perceives an observation, which is then used to update the belief using a particle filter. Now, if these steps are performed in a strictly sequential manner, there would be large delays after the robot has executed an action due to the time needed to update the belief and compute a policy from the updated belief. So what we do here is to reduce these delays to a minimum. We parallelize these steps wherever possible. And this works as follows. So suppose the robot is currently executing an action from the current belief. Now at the same time, we keep on improving the policy from the current belief. And the way we do this is we sample additional histories starting from the current belief, but make sure that the first action in those histories is the action that is currently being executed. So in other words, we keep on improving the policy in the subtree following the currently executed action, where here we assume that executing an action takes roughly 0.7 seconds. Now at the same time, we can start to update the belief. And as I mentioned before, ABT is using a particle filter, which consists of two steps. So the first one is sampling particles using the currently executed action. And the second step is updating the weights of the particles once the robot perceives an observation. Now, while the robot is executing an action, we can already sample these particles. And then, once the robot perceives an observation, all that remains is updating the weights of the particles, which can be done fast. Okay, so now in case we end up in a belief that hasn't been encountered during planning yet, what we do is we interrupt the whole process and we give it 1 second to compute a policy for the new belief. Okay, so after we've seen the entire problem and we've seen how we solve it, just a few words regarding the perception system. So here we are using methods that are pretty much off the shelf, where we have a convolutional neural network in conjunction with a point cloud algorithm. However, as I mentioned before, since we do very little calibration of the Kinect sensor, there are substantial perception errors with respect to the location of the cup. Okay, so what we did now to evaluate our system is we first tested it on the picking problem, where we conducted experimental runs in which we changed the position of the cup multiple times during runtime. We then tested our system with and without macro actions, And in addition to that, we also tested a deterministic motion planner, RT Connect, to get a baseline reference. And as we can see, RT Connect achieved a success rate of only 35% because it essentially ignores all the uncertainties with respect to the location of the cup. Whereas our POMDP-based planner achieved a success rate of at least 95%. However, once we start to change the position of the cup during runtime and the robot had no access to the macro actions, none of the runs were successful anymore. Because due to the limited planning horizon, the robot couldn't figure out that it had to use additional scanning actions to relocalize the cup. Whereas with the macro actions, we achieved a success rate of at least 90%. Okay, so as I mentioned in the beginning, we showcased our system at last year's SIMPA and ICRA conferences. And for this, we modeled and implemented our system using OPPT, our POMDP software framework that I talked about yesterday's demo session. And then we ran the entire problem in 7 consecutive days. So out of approximately 150 runs, we achieved a success rate of more than 98%. Which essentially shows that, yes, POMDPs can be made tractable for such complex physical robot scenarios. Okay, and then before I finished, let me just quickly show you a video, how this works or how this looks like in practice. So here we are basically looking at the problem scenario where we are changing the position of the cup multiple times during runtime. So it tries to approach the cup, we change it, and then it's using the macro action to execute a scan action for relocalization. Then it basically replans. We're a little bit mean, change the position again. And then basically what we do now is we remove the cup from the table so that the robot doesn't see the table anymore. It performs a retract action because it assumes, okay, I need to get away from the table in order to localize the cup. And then last but not least, it picks up that cup. Now we also tested our system in mildly cluttered environments. So when we have multiple obstacles positioned on the table, which worked quite nicely as well. And then after this, we have the complete run during our demo session at the SIMPA and ICRA conferences, where we allowed bystanders to put the cup on random positions on the table, and the robot basically had to figure out how to grasp and pick up the cup. So then it tries to position the cup in an orientation that is beneficial for scooping. Then it's doing the actual scooping. So now this is pretty shallow because like the candy surface is pretty low, and the robot also tries to avoid collisions with the bottom of the candy box. And then last but not least, it's putting the cup back on the table. Now we have an additional video with bystanders this time. Okay, and with that, I'm already finished, and then I'm looking forward to answer your questions. Thank you very much.
How often do you have to recompute the policy?
How often we have to recompute the policy? So it usually happens after a retract action when the robot doesn't see the cup, because like basically the way we do the belief update when a grasp fails, we assume that the robot has no information whatsoever where the cup is located. So basically the subsequent belief becomes a uniform distribution over the entire table. So now once the robot then scans the environment and basically perceives an observation regarding the location of the cup, then we end up in a belief that is much different than the uniform distribution. So that's usually a case then when we recompute a policy.
Thank you for the talk. So in your data, when you had 0 movements, you still had 95% without the macro actions, but 100% with the macro actions. So did the macro actions help out, or was it just chance that?
Well, it was just, I would say that was just chance, because like if you look at the, basically at the data set, we conducted 20 runs for each scenario. So I would assume if you were running more runs, then that would sort of even out. And we also saw that in the live demo, where we basically had more than 150 runs, and we achieved a success rate of 98%. So that's just due to the limited data set.
A couple of questions. One would be, how do you discretize the continuous variables in your state space?
So our state space is continuous. As I mentioned before, we have a hybrid space, which consists of several components, where the first component are the joint angles, which is basically operating in a continuous space. So the other variables, the gripper state and grasp state, these are discrete states. So basically we have a continuous action space, continuous observation space, but we have a discrete action space. Because at the moment, solving POMDPs with continuous action spaces is still sort of very early research. So we decided that we keep the action set discrete, basically.
So the other question would be, when you have these macro actions, it affects the belief state that you encounter after the macro actions, right? So you don't get all possible belief states. Do you use that fact to make your search better?
Yeah. So basically, yes, you are right. We don't encounter all the belief states after a macro action is being executed. So basically, the whole idea of that macro action is really to reduce the planning horizon. Now, the way these macro actions are implemented, you can see them as a conditional plan, because they are conditioned on the observation you are actually getting after the after a scan action, right? So it is essentially, it is a conditional plan, and during planning, it then figures out, okay, if I do a scan action and then I get close to the cup, wherever your observation puts that cup, it figures out, okay, it actually helps me to reduce uncertainty. But the actual realization of that macro action then depends on the actual observation that you're getting during during execution.
Okay, now we can thank the speaker again. We can switch to the next presentation that is about trajectory tracking control for robotic vehicles using counterexample guided training of neural network. And the speaker is Sriram. You can, yes, explain your name.
All right, can you hear me? Perfect. All right, so thank you for that introduction. This is joint work with Arthur Claviere, who's at École Polytechnique. This work was done when he was visiting us at University of Colorado, and with my PhD student, Souradeep Dutta, who's currently at Toyota, so he couldn't make it here. So the main problem we would like to solve here is one of what we call robust trajectory tracking. So what is robust trajectory tracking? So let's say you have a very common situation where you have a vehicle and you have a trajectory that you would like to follow. But you would like to follow this trajectory robustly, in the sense that if your initial position is anywhere inside the blue circle, you would like to end up somewhere inside the red circle at the end of following the trajectory. And by the way, while following the trajectory, you need to be inside the gray tube. In formal verification, we all know this is an example of a combination of a safety and a liveness property. I would like to reach from the blue tube from the blue circle to the red circle while staying somehow inside the gray tube as I am doing that. So that's my overall goal, and we call this robust trajectory tracking. And I would like to do this in the following setting. So the vehicle itself, I model as a system of differential equation, dx dt equals fx uw, x being my state of the system, u being the control input, and w being the disturbance input. It's a very standard control theoretic formulation. The disturbance includes things like wind that can disturb the current state. The controls includes steering input, throttle inputs, things that can change the velocity and the orientation of the vehicle. So my goal is to compute that feedback, u equals g of x, so that from any given state, I know what control to apply immediately. Even though I have formulated this in continuous time, most of the implementation in the paper happens in discrete time, but that's something that we did for implementation. The theory works in continuous time as well. Okay. And the main idea here is to make up a library of primitives that are sometimes called maneuver libraries or maneuver automata in robotics. And here, the idea would be, given a vehicle state, I would like to synthesize a bunch of robust trajectories offline. So before I do any kind of deployment, I would like to have these robust trajectories as a library. And as I am running, the planner is allowed to plan only using these robust trajectories. So this idea goes back to work done by Emilio Frazzoli back in 2005. And there has been significant amount of follow-on work for this idea of robust planning using robust trajectory tracking. So at a high level, there is a planner at the top level which plans and tells you to follow one of these trajectories robustly, and then at the bottom layer, there is a controller that follows that trajectory, and then the planner chooses a new trajectory to follow, but it always chooses in this library of robust trajectories. So that's the overall setup, but I'm going to focus on a single trajectory, so just following a single given trajectory with some robustness specification around that trajectory. So part of this is also that we are going to use neural networks to provide this feedback. So this g of x function is going to be realized by a neural network. And the challenges are, it's a nonlinear plant model in general. It has disturbances. The disturbances not just model wind and things like that. It can also model uncaptured dynamics of the system, or sometimes modeled as disturbances. So typically, the control feedback has to be nonlinear. And we need to guarantee that this feedback is robust. And we are going to try to find a feed-forward neural network that implements this function g. So you may ask, it's the end of the day, why am I annoying you with neural networks? Well, there are many reasons. The usual reasons: neural networks are universal function approximators. So if there is a continuous feedback, then you will be able to find a neural network that approximates it to arbitrary precision. Everyone says that it's like a standard formula you repeat whenever someone forces you to a corner. But there are more interesting reasons from control itself. For instance, you can view this as a form of what we call explicit model predictive control. There are theorems which show that if your system is linear, you will find a control that's realized by a very simple single layer neural network with ReLU units. That's a very well-known theorem. People do that explicitly in the form of a table, but you can do it compactly in a neural network. So neural networks are very compact representations in that way. And finally, neural networks are easy to learn if you have the data. But the challenge here is, how do we learn a neural network that guarantees this kind of robustness? All right. So basically, there are two ideas in this paper. The first idea is we are going to use a demonstrator to provide us the data from which we are going to train this neural network. So it's some form of an imitation learning, where the demonstration is provided by a form of a controller called a nonlinear model predictive controller. So we are going to deploy an MPC, and we are going to use that MPC to train our neural network, number one. But number two is we are going to use a counterexample guided training, which means that we are not blindly mimicking the MPC. We will train some initial neural network, and then we will try to falsify that network. We'll get some data from the falsification, and we'll keep training this in a loop. As I will explain in a second, we show a few experiments in simulation on some UAV models with large state space and ground vehicle models. All right. So this is the basic idea behind the paper. We have a demonstrator. Let's call this a component, which if you give me a state, of the system, it tells me what control to apply immediately, so that in the future I can keep the system from robustly following the trajectory. So it is a demonstrator that's telling me how to do the control right at any point. I give some initial state samples to this demonstrator, and I get some data. And throughout this talk, data to me is state control pairs. So I have state, I have the corresponding control, comes from the demonstrator. And then I have this box which aggregates all the training data. You will see where else the data will come from in a second. Of course, I use an off-the-shelf neural network training. Neural networks are just a stand-in. You can replace it by any data-driven model that's universal, that can capture the class of functions I'm trying to learn. So it's not important that we do it with neural networks, but neural networks are very popular these days, so we use neural networks. Okay, so we get a candidate neural network. And here's the most important thing. We try to falsify this neural network. So we are going to search for counterexamples. With this neural network as the controller, we try and find trajectories of the system that violate our robustness requirement. If we find such counterexamples, we can send those counterexample states back to our demonstrator, which gives us more data. So on those counterexample states, we will run the demonstrator, which demonstrates the correct control. Presumably, the neural network's control is wrong on those states, so it demonstrates the correct control. We aggregate this training data, keep going around the circle. When do we stop? We stop if we run out of patience, or at some point, the falsification search says, I cannot find any counterexamples. We stop. So that's the overall picture in this paper. It follows a very well thought out idea in this area of formal synthesis. It's called counterexample guided synthesis. There is a lot of work on counterexample guided verification. It's inspired by that. And the main idea here is we are using it to try and learn models from data, as opposed to doing it exactly in the sense formal methods people do. So that's the overall setup. So let me go into a little bit more detail on this setup. So to reiterate, my problem inputs are the dynamics of the system. I provide the specification in terms of the desired trajectory. Typically, we would provide some waypoints that we want to hit at various times. And we'll assume that it's a straight line joining these waypoints is the trajectory we want. And we provide a radius rho. So the tube is defined as all points that are within rho distance of this piecewise linear trajectory. And we have an initial set of states I, which is shown in green, and then a target set T. So the green circle all the way to the red circle while staying inside the green tube. Okay, so that's the overall specification. We could write it out in temporal logic, but there is no need. It's simple enough to show it in a picture. And let me get to the next component, which is the model predictive controller. So what's a model predictive controller? So a model predictive controller is a way of solving for a control to be applied to a dynamical system based on a cost function. So just to demonstrate it in terms of pictures, suppose I have my desired trajectory and I have my robot or my vehicle. It has a position. Let's say I am interested in nullifying that lateral deviation between where I'm supposed to be and where I am. In model predictive control, we consider a finite time horizon. So it's basically finite horizon planning done on differential equations or continuous state spaces. So let me apply U1, and suppose I get to x1, then I apply U2, I get to x2, then apply U3, I get to x3 and x4. So I imagine a finite time horizon into the future. And so this U1, U2, U3 are my unknown control inputs. I don't know what they are. Correspondingly, x1, x2, x3 would be my unknown future states. I define a cost function, so that's that math on your right. So C, x0, x1 through xk, k being my time horizon now. U1, U0 to UK minus 1, which are the controls I apply. These are all unknown. So minimize this cost. And then I have written down here, I just wrote down a simple Euler discretization of my dynamics. How do I get x1 from x0? How do I get x2 from x1? By applying the dynamics. And tau c here is the time step I'm using. So this is the discrete version. There's also the continuous version, which I can write down. It involves integration instead of summation, stuff like that. But I will spare you the details. It's late enough in the afternoon. OK, so this is the demonstrator. And once you have all of this, you would get U1, U2, U3. You will forget about U2 and U3 and just apply U1. And then wake up again after a little bit of time and solve the whole problem again. Even though you get this whole sequence, you just apply the very first control and forget about it. And then come back and then compute this whole thing again, apply the very first control. And that's very, very important for getting robustness and all that. All right. So given that we have an MPC controller, we can build an MPC controller for trajectory tracking or robust trajectory tracking. The way we do it is we try and get some finite time horizon. We look ahead from finite number of waypoints. And we design a cost function that's going to help us be robust. It doesn't guarantee that we solve this robust control. But what we can do is design this MPC. And often enough, it works. And it serves to demonstrate from any state the right kind of control to apply on that state so that I can nullify the deviation between where I am and where I'm supposed to be quite quickly. Okay, so this is quite standard so far. So the interesting thing here is we are going to now apply the MPC with a falsification search. So what is this falsification search? So the goal behind falsification search is, suppose I am given my current neural network candidate. So I have my candidate neural network that has been learned from the current data. My goal is to see where does the network go wrong. So I consider the network in feedback with the ODE or the dynamics of my system. And I would like to find a red initial condition and some disturbances, which I can't show. But there are some disturbances, let's say, such that the resulting trajectory violates my robustness specification. So falsification is the problem of finding counterexamples. Given a system, given a property, I'm interested in finding counterexamples. So how do we find counterexamples? Bad news first, it's undecidable. Like everything else in verification, falsification is undecidable. And it's undecidable even for very simple dynamics, like linear systems, it's undecidable already. What am I doing talking about nonlinear systems? And then nonlinear systems in a feedback with a neural network, it's kind of hopeless. And there are many challenges. You can think of it as a planning problem on a continuous state space, if you will. But unlike planning problems, the solutions here involve corner case behaviors. You get very few or no solutions. They are usually very difficult to find. The solutions are isolated from each other in the search space. So it's very difficult, general, to find solutions. Though recently there has been a lot of progress on applying ideas from planning, applying ideas from optimization to find falsifications. There are some tools I can mention, like Estalero and Breach, that have been successful. They have been used to find bugs in industrial control systems. So they are kind of popular. But in this paper, we use a different kind of falsification that simply poses the falsification also as an MPC, except that the control is now given to the disturbance and the choice of the initial condition. So you just flip it around. And the cost function, instead of keeping you inside the tube, tries to push you outside the tube. So we just flip the cost function. We just flip the roles of the control and the disturbance. And we implement the entire falsification search as a model predictive control. The details are in the paper. But roughly, we identify a critical point and a critical direction that we would like to move the trajectory along. And we do something that is exactly backpropagation. We unroll the neural network's end steps. We do a backpropagation. It's very, very uncannily exactly like backpropagation, except it's trying to disrupt the system instead of trying to train the system. And we get a gradient vector for the disturbance, for the initial condition. The calculation is all spelled out in the paper. And then we use one step of gradient search. You can put this all in a computation graph, put it inside your favorite solver, TensorFlow, PyTorch, and it will solve it for you. That's the nice part, okay? So these are pretty standard now. The interesting part now comes about when we talk about how do we combine data. So remember, at each step, we have the initial training data, and then we get the counterexamples we found in iteration 1. So we retrain the network, we get a counterexamples in iteration 2, and all the way to iteration n. You have to somehow combine these counterexamples in a clever way if you want your network to learn. At one extreme, if you ignore the counterexamples, you're not going to learn. On the other hand, if you just train your network on the new counterexamples, what will happen is it might oscillate between counterexample number 1 versus counterexample number 2, and then go back to counterexample number 1. It's like, if you try to fix this side, things might break this side. If you try to fix this side, things might break that side. And we have seen that behavior. So somehow you need a way to combine counterexamples from each iteration to create the data set for the n+1th iteration. This is an open challenge. So we tried different ideas. From imitation learning, there are ideas like Dagger, and there is no single rule that we could find. The best we could find was to fix a number of samples at each round, fix that many counterexample states, query the MPC on those sample states, and merge them with the existing data set. So it's pretty ad hoc. It's inspired by Dagger, if you want to know. Dagger is a very popular imitation learning paper by Ross et al. Back in 2000, and I have a citation. It'll come up 2011, I believe. So it was inspired by Dagger, but the setup for Dagger and the theorems that were proved in the Dagger don't hold for us. So it's a very difficult question. What's the strategy? So this is something we tried. We found it to be successful, but the full answer to what's the best combination strategy probably requires much more analysis. So some benchmarks and preliminary evaluations. So we tried a 2-wheeled vehicle with 4 state variables and 2 control inputs, nonlinear ODE model of a quadrotor with about 12 state variables and 4 control inputs there. We did an evaluation of our gradient-based falsification search against other strategies, including just random search or just an exhaustive grid search of the space of initial conditions and disturbances, which was quite exhaustive, didn't finish in many cases. So there we found that our gradient-based falsification search was quite good, in fact, really good at finding falsifications, much better than other techniques we tried. And we also tested our system end-to-end to see if it could successfully train neural networks with varying network topologies against trajectories where we varied the curvature, the Gaussian curvature of the trajectory as a measure of how difficult it would be to move the vehicle along the trajectory. We have an implementation of our approach. So just to give you a couple of pictures, it's all in simulations at this point. We haven't tried any of this on a real platform. But you can see an example of a trajectory following a 3-dimensional trajectory following for a UAV. And on the left, you see some intermediate states. Those arrows show the directions in which we are trying to move those intermediate trajectories. On the very right, you see the final endpoint, some of the simulations of the final endpoint. And you see that the final endpoints don't explore the entire tube. They explore like a very small fraction of the tube, and they converge very quickly to the actual reference trajectory. I have a slide on comparing falsification search strategies, but too many numbers. The details are in the paper, and they basically show that our search, the gradient-based search, is much more powerful. Very surprisingly, the grid search, if you discretize and do a grid search, it doesn't work so well. We don't know. So we studied some preliminary effects on network topology. This is something that I did not personally want to do, but we had to study how the varying network topologies affect the results. But then we got a very surprising result. We found that the simplest and the smallest network, a single layer network with about 10 neurons, was the most successful in all the experiments we tried. Networks with 4 layers or more than 4 layers failed miserably. And we think the reason is when you have a larger network, they have so many more behaviors that the falsification search is always able to find a falsification, and the technique just runs out of time. Okay? So in terms of conclusions and future work, So far, our work has been empirical. We haven't proved any convergence results. We haven't done a complete analysis. So there needs to be a lot more work, as I said, on strategies for combining counterexamples with the initial sampling data to come up with a convergent scheme here. Effect of neural network topology is another, and then trying to show how our technique can handle model mismatches and stuff. There's also comparison with imitation learning approaches. We are not quite doing imitation learning. There's a big difference that will take some time to explain, but I'm happy to explain if you ask me. And so we need to compare with very similar techniques like Dagger and Plato, but they are imitation learning approaches, and there is a big difference in the setup. So these are things that we would like to do for the future work. Thank you so much for listening to me, and some acknowledgements to people who paid us the money.
Is there a relationship between the number of neurons and the number of dimensions in the state space in the dynamics model?
No, so we didn't find any big relation. So we found that for the UAV, we needed slightly bigger networks because the state space was slightly bigger. But other than that, we didn't find any relation at all. We were expecting like we would need networks with 10 layers, 1,000 neurons. Those failed miserably, so we don't even report on those. Yeah, networks, where the biggest network was 3 layers or 4 layers.
Is there a relationship between the class of disturbances that you are becoming robust to and the choice to do falsification by flipping control and disturbance?
Yes. Obviously, so one of the important things is if, the disturbance and the choice of the initial conditions are the things that are, so if you imagine it as a game between an adversary and a controller, the adversary controls the disturbance. So if you give the adversary more, like a bigger disturbance set to choose from, obviously you would get more and more falsifications. So now what's the right disturbance set to choose? That's something we couldn't figure out. So we have some like fixed numbers in the paper, but not more than that. But ideally, we need to account for wind disturbances, and we also need to account for unmodeled dynamics. So most control is not done under the robust setting, so it's very difficult to get references from other papers on what they use. So.
Thank you very much for a nice talk. I was wondering, did you compare this with some other control methods for robust control, like H-infinite, or, because it's really interesting robust control method that you're proposing.
We didn't do H-infinity, we did LQR, which is the easiest one to compare against. So with LQR, we get good performance, but we are also able to falsify it quite easily, so we didn't pursue that any further. The problem with LQR is you need to do a linearization. But if you have a trajectory, your linearization is a time-varying linearization. So it's very difficult to do LQR for that. And if you do a very naive linearization just around the initial states, your LQR just fails miserably when you apply to the nonlinear model. So it's not very nice to do that, right?
Yeah, I agree with LQR. Maybe LQG, like.
Yeah, so we need to try those things. But with trajectory tracking, you have to do a time-varying. You have to solve a time-varying problem. I don't know any tools for time-varying Riccati equations, so it gets a little difficult for us. But those comparisons, we owe those comparisons for sure. Yeah, we haven't done them.
Thank you.
Questions? So we can thank again the speaker.
Thank you.
And close the session.